Do one of these questions by one of my students. So this question is a bit of a weird one. It's actually very simple. What they've actually done is they've combined enthalpy of hydration with a Born-Haber question. But the principles of Born-Haber stay exactly the same. So usually whenever you're doing a Born-Haber, part one is nice and easy. What you always do is you just fill out every single step, first by writing out the equation and writing in the numbers for it. So general rules of Born-Haber, each step, only one thing can happen. So in this arrow and all of these arrows, only one thing can happen per step. So if you look at this arrow here, this is just your compound. So usually above your compound, the first line will always be enthalpy of formation. So a formation formula. So that would be Mg plus Br2. Now remember, this is going to go into MgBr2. When it comes to enthalpy of formation, you have to have one mole of product. So because you have to have one mole of product, you're going to leave it as MgBr2. You don't need to balance anything, so you're just going to leave it as that. To put in your state symbols as well, this will be solid, this will be gas. What has happened here is this has been bond dissociation enthalpy. Why is it not atomization energy? Because atomization energy produces 1 mole of Br, whereas here we have 2. The next step after that is atomization of magnesium. You produce your gaseous magnesium. This thing here is your first ionization energy. This step here is your second ionization energy. Because you see there's a 2 plus here, you know that it must be ionized 2 times. So that will be your second ionization energy. With the formula would be Mg plus, sorry, because you've lost 2 electrons, that will now be Mg 2 plus 2e minus plus 2br. Cool, because now this shows that you have lost 2 electrons. Like, the next thing that you need to do is that's all done. Okay, now the question says calculate the enthalpy change of hydration of bromide ions. Okay, first things first, we need to identify what step are they talking about here. Using your Born-Haber cycle, calculate one of the enthalpy change of hydration of bromide ions. Okay, what step are they talking about? Okay, let's see. Enthalpy change of hydration. This comes to do with the earlier part of this topic. I'm just going to give you a quick detour and just explain what this is about. In enthalpy change of solution, 2 things are actually no. Yeah. In enthalpy change of solution, that is the enthalpy change when you have a solid ionic compound going into its aqueous ions. So when you have a solid ionic compound going into aqueous ions. This itself has 2 steps. The first one being the lattice enthalpy of dissociation, which is when your solid ionic compound gets broken down into its gaseous ions. So not into its aqueous ions, into its gaseous ions. This is the lattice dissociation enthalpy. Enthalpy of hydration is when your gaseous ions turn into aqueous ions. Enthalpy of hydration is when your gaseous ions turn into aqueous ions. So this question is asking you, calculate the enthalpy change of hydration of bromide ions. This is when your bromide ion is going from its gaseous ions to its aqueous ions. That's what a change of hydration means. So take a minute, pause the video, look at all these arrows. Which arrow does that represent? That represents this very last arrow down here. Because as you can see, the difference between in this arrow is your bromine is going from a gas to an aqueous. This is the arrow that they want you to work out. I hope that makes sense. Cool. Right, so now what you do is the same with all the other Born-Haber questions. You just fill in all these gaps and you just write the numbers in. So let's go through the top. First ionization energy of magnesium. Let me zoom out a bit. So first ionization energy of magnesium is 736. So I'm going to write 736. Where am I going to write that? Have a think where you're going to write that. You're going to write that over here. Make sure you don't write that over here because this represents second. Okay, second ionization energy of magnesium is 1450. So you're going to write that over here. Atomization of bromine. Remember, atomization of bromine is when you go from bromine, when you produce 1 mole of bromine gas. Which step does that have a think? That is this step here. You're going from Br2 to Br. You've separated the bromine atoms. But atomization produces 1 bromine. Here you have 2 bromine gases being produced. So you're going to get your atomization energy, which is 112, and you're going to times it by 2 to get 224. Hopefully that makes sense. If it doesn't make sense, the student can message me. So it goes into 224. The next thing is atomization of magnesium. That's 148. That's just solid to gas. So 148 here. The next thing is electron affinity of bromine, which is when 1 bromine atom accepts 1 electron. Here, however, we have 2 bromine atoms, each accepting 1 electron. So it's still first electron affinity because they're each accepting one electron. But because you have two atoms accepting this, your electron affinity of bromine, which is minus 325, you're going to times that by 2. And you're going to get minus 650. Okay. Formation of magnesium bromide is minus 525. That represents your formation formula. So that here is minus 525. Make sure, by the way, that all your negatives and your signs are all okay. Hydration of bromine ion, that's your X. Hydration of magnesium ion. Remember, what did we define hydration as? Your ion goes from gas to aqueous. And this is for magnesium. So take a look, which one would that be? It's got to be this long step here. So that is minus 1926. And the solution of magnesium bromide. Now, enthalpy of solution, if you look at the way we defined it, it's when, remember I said at the beginning, it's when your ionic compound goes into its aqueous ion. Look at this. Ionic compound, aqueous ions. Ionic compound, I don't think you can see my mouse, but what I'm saying here is ionic compound into your gaseous ions. Hopefully that makes sense. Whereas your enthalpy of hydration is gaseous atoms into aqueous ions. Cool. So ionic compound into its aqueous ions. Which step does that? Which step represents that? Here, ionic compound, aqueous ions. So this here would be the solution of magnesium bromide, which is minus 186. So you were right, minus 186 here. Okay, from here on out, it's nice and easy. In order to get X, you just go around. General rule with a bond haber, it is that it is a cycle. So you're trying to go from this step. I'm just going to put that in a different color to make it easy for you to see. You're trying to go from this step down to this step in this way. But you don't know this yet. So now think, what is a different way, a different route that you can take to get from this step here to this step? The different route that you can take is as follows. You can go the long way. So you can go up, then down, 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 down. So do you see how you still started here and you still ended up here? The reason why we go this way is because we know every single number. You know every single number. So this is why we go this way. We go this way around instead. Hopefully that makes sense. If it doesn't, again, message me and I'll clarify. Okay, let's carry on. Okay, fine. So this part here is X. So we mentioned that this X is going to equal you going around all of this way. Okay, so now let's take this step by step. You need to go up here. Your arrow, however, is pointing down, but you're going up. So the arrow that was pointing down was equal to minus 1926. If you're going up, that's going to be positive 1926. Same thing here. You're going down, but you need to go up. So the arrow for going down was minus 650. So up was positive 650. And then remember, we're going round. So the arrow is pointing up, but you're going down. So that's minus 1450. Then you're going down again. So that's minus 736. Then you're going down again. So that's minus 148. Then you're going down again. So that's minus 224. Then you're going down, which is the same as this arrow. So it's still minus 525. And for some reason, I forgot to write the last one. It should have been minus 186. And you're still going down. So it's still minus 186. So now you've come up with an equation. You're just going to plug that into your calculator. And now you've worked that out. So you do 1926. Everyone plug that in your calculator just to make sure I haven't made a mistake. Minus 1450. Minus 73. I think that was 736. Minus 148. Minus 224. Minus 525. Minus 186. And your answer is minus 693. Cool. We're still not done. This X represents you dissolving 2 bromine ions from gas to aqueous. The question wants you to work out, to calculate the enthalpy of rotation of bromide ions that referring to 1 bromide ion. So X is minus 693, but that represents 2 Br minus gas going into 2 Br minus aqueous. You want 1 Br minus, because that's what enthalpy of hydration is. It's just for 1. So therefore, you just divide this by 2, and you should get like minus 300 something, minus 346.5. And that's it. That's how you do this question. Hopefully that makes sense. The next question, write an equation for the lattice enthalpy of magnesium bromide. Calculate the lattice enthalpy. Okay, this is a very good question. Lattice enthalpy of magnesium bromide. The thing with bond Haber cycles is you have to understand, what do these words mean? What does lattice enthalpy of magnesium bromide mean? Lattice enthalpy of magnesium bromide means you are forming magnesium bromide from its gaseous atoms. So it's a sort of step when you are going from the gaseous ions. So you're going from the gaseous ions to magnesium bromide. So what are the gaseous ions? It's Mg2 plus and 2Br minus. So you're going from the gaseous ions to the compound. Hopefully that makes sense. This is how we define. This is what lattice enthalpy means. From the gaseous ions to the solid ionic compound. Now, all we do is we just look at our Born-Haber cycle and we look here. Which step shows this? I'll give you that. Pause the video, take a look. Which step shows that? It's actually no step. There's no step directly going from gaseous ions to solid. Your solid is over here. Where are your gaseous ions? Up here. There's no step going from there at all. So you want to go from here to here. So you want to go from this step to this step. But there's no step for that. So again, this is the beautiful thing with, like, this is the fun parts with cycles. You just go around. So you can't go this way directly. If any of you have done GCSE vectors, then this will make a lot of sense. You can't go that way directly. But you can go either up, down, left, and then down. Or you can also go down, left, and then up. Both ways are fine. We'll do the yellow way because it's a bit shorter. So you're trying to get there. So you do minus 1926. Remember, you want to go down, and the arrow is already pointing down. So we're going to keep the minus 1926. We're going to go down to the x. We just worked out what x is. X was minus 693. Remember, minus 346 was for 1, but the actual x was minus 693. Then you're going to go up. Now, down, the arrow down was minus 186. So now if you're going up, you've got to make that positive 186. And whatever that answer is, that would be your answer. So 1 minus 693 plus 186. And that is your answer, minus 2432 minus 2433. And that should be your answer. Okay, I hope this makes sense. If you guys still have questions, just let me know now, and I'm more than happy to answer it.